I just want to inform you that I have shifted from Banaras University to University of Allahabad in August 2022, and I am going to discuss about the materials for clean energy generation and storage. This materials is related to the hydrogen storage and the hydrogen production. So, as you can see this slide, we need energy in our daily life and the part of our system, because everything is running with the help of energy. For example, our mobile or this micro devices, and for example this devices, laptop and other things. So we need energy. And what is the situation of energy? If you see the energy crisis we are facing the energy crisis. For example, in the case of developing country like India and China, our energy crisis is going increases every day. And for example, in the case of developing country, for example, USA and other UK or other European country, the energy demand is almost saturated. But if we use this energy from the fossil fuel, for example, coal and oils or natural gases, so the storage and the amount of this type of energy is going to be finished very soon in future. And what is the other problems when you are using this kind of energy is emission of greenhouse gases. For example, CO2. CO2 is a very problematic gases for increasing the global warming. If you see, if CO2 layer formation is taking place around the Earth, and when infrared is coming from the sun, it will be absorbed, and this increases the temperature of the Earth, and this creates the global warming effect. If you see here, this kind of global warming is getting a lot of problems. This is the example of the Thailand flood in 2011. Whole the city was covered under the flood, and the glaciers melting is the direct effect of global warming. And you can say that this kind of global warming is the future terrorist of the humankind, because in the terroristic activities, the human is facing problem, and this global warming is also a similar kind of things where you can face a lot of problems. And if you see the global warming effect in India, and our mountain area, glaciers melting is taking place, and so much flood is coming every year. For example, this year also, so much last year, so much flood in the several cities was there, and this directly affect our agricultural productions. And you know, in India, we are just our problems. You can see here also in Chennai and Kochi in different times, so much flood is taking place. And if you see the direct air pollutions, if you see the vehicle number of vehicles increasing day by day, and this type of crowd are available. You can see in the Delhi road. If you compare this situation, the officers are going by bicycle in 1945 in Delhi. But if you see, if you compare today, this type of crowd you can see every day on the Delhi road. So this creates lot of pollution, air pollutions. And what is the effect of the air pollution? You can also observe with the help of this several news on the newspaper. And other country, for example, China is also facing a lot of problems due to this type of air pollution. If you see here, our health is also affected, and our life is directly affected with the global warming, or DGP is also directly affected by this kind of air pollution and the global warming. The last year also there was a news that this type of air pollution is directly affected our human health. So this is not good, and everybody is thinking about this kind of global warming and this type of air pollution. Or ministry is also. So where is the solution? Solution is the renewable energy, and Dr. Sanjay Srivastava has already discussed about the one kind of renewable energy, the solar energy. This solar energy is quite good, but this is also some limitations. So I will discuss about the limitations. For example, other energy is a nuclear energy, but this nuclear energy also has some limitations. For example, this incident in 2011 in Japan, it just attracted to think about this nuclear energy. And where is the solution? Solution is renewable energy. Of course, one is solar energy, also is the wind power energy, ocean energy, hydropower energy, geothermal energy, and hydrogen energy. So many other renewable energy is there. But our main focus is on the hydrogen energy. I want to discuss something about this, because if you compare about the fuel efficiency of the hydrogen with respect to other hydrocarbon fuel, so it is almost 3 times better than the petrol or other hydrocarbon fuels. But if you compare about the toxicity is zero. So hydrogen has no toxicity, and we can use hydrogen as a fuel just like a hydrocarbon fuel like petrol. And we can generate the hydrogen with the help of solar energy or wind energy or some other energy also, and we can use this just like the water, and we can produce the hydrogen by the electrolysis, and the solar energy is completely clean, and there is no kind of pollutions. And when we burn the hydrogen in the presence of oxygen, we can get the hydrogen and energy. So we can produce the hydrogen with the help of water, and using some other energy sources like solar energy, and we can again get the water. So this is completely a cycle. So you can burn the hydrogen in the presence of oxygen, and you can get the water, and again you can just use this water and you can produce the hydrogen. So in early stage, India was not very focused, but in 15 August 2021, our Honorable Prime Minister has declared the hydrogen energy mission. So I was also in the draft committee, member of the draft committee. So now the government of India is also trying to focus on the hydrogen energy, and I hope that in future the main goal to cut the net energy carbon zero. And I think in December also here there was a conference to net carbon zero in 2070. So we are just trying in this direction. So the government has already declared that three hydrogen hub, and they just launched a project, and I hope that in very soon the 3 hydrogen energy hub means every city is just using the hydrogen energy as a energy source. So and government of India has already declared that we have to cut the conventional fuel based on the fossil fuel. So where is the issue? Why we are not able to use this hydrogen energy? So there is 3 kind of things basically to use the hydrogen energy: hydrogen productions and hydrogen storage, because fuel efficiency is very high and the density of the hydrogen is very low. So on the basis of leakage, it is quite dangerous compared to the other fuel. And the other is application. So application part is almost developed at several places in several countries also, at Varanasi University also. But still the hydrogen production is the main issue, and the hydrogen storage is the main issue, because you cannot store the hydrogen like a high pressure gaseous cylinder, because the fuel efficiency is quite high and density is quite low. So we can generate the hydrogen, we are produce the hydrogen using different methods, but main focus is how to generate the hydrogen using clean energy. Because if you are using hydrogen, you are producing hydrogen using coal, this is not very useful for the environment. So main focus is from where you can generate the hydrogen. There is so many methods. You can use the natural gases, steam reforming of methanol or other things, biomass steam reforming technology, biomass gasifications, and electrolysis. So electrolysis is the main things you can say in the category of green hydrogen production. So many category of hydrogen production, for example, blue, gray, black, and purple. So when you are using, when you are producing hydrogen using coal, this is under black hydrogen production. But our main focus is to produce the hydrogen using green category. So this is the hydrogen production using green category. You can use the solar light, because this solar light is freely available, and you can produce by the water electrolysis of the hydrogen. But you should store the hydrogen in a safest mode. So we are just trying to show some examples how to produce hydrogen using electrolysis, and also how to store the hydrogen in the safest mode. This is the general process. We are not going to discuss in details. But I have used some special kind of material, say quasi crystals. So I just want to say something about the quasi crystals. This quasi crystal was discovered in 1982, 10 April 1982, but the paper was published after 2 years. And the said man discovered has got the Nobel Prize in 2011 in chemistry. So this quasi-crystalline material is the aperiodic materials. Before 82, there was a concept that 5-fold symmetry and 10-fold symmetry are under the forbidden symmetry category. But in 82, the said man has just discovered a special kind of materials in an aluminum magnesium alloy. They have just selected the aluminum 86 Mn14, and after rapid solidification, they have got the 5-fold symmetry, nice 5-fold symmetry in this kind of materials. So after later on, some other scientists, one scientist is from India also, and from Upadhyay, Bangalore, has discovered the 10-fold symmetry. So this is the nice example of the 5-fold symmetry, where you can got the different type of diffraction pattern. This is the along 3-fold, this is along 2-fold, this is along 5-fold, and in same kind of materials, in some other material also, you can get the 10-fold symmetry. For example, this is called the decagonal quasi-crystals, and this is called icosahedral quasi-crystals. So I have used these both kind of materials for hydrogen production as well as hydrogen storage as a catalyst. I just want to say that the Lord Penrose had discovered this 5-fold symmetry mathematically in 1978 by the tiling of two types of rhombus. And of course, they have got the Nobel Prize in 2020, but not for this kind of work, for the different work in physics. So this is a nice example, model of the decagonal quasi-crystal as well as icosahedral quasi-crystal. So this is the structure of the icosahedral clusters, where you can get the 5-fold, 2-fold, and 3-fold. But in the case of decagonal, the basic structure is like that. You can get only 10-fold and 2-fold. So this fold means orientation is also very important. Playing important role. So we have just trying to make the two-dimensional of these quasi-crystalline materials. So basically, two-dimensional quasi-crystalline material was discovered in aluminum, palladium, manganese, and aluminum, copper, cobalt. Only two systems, and this is the so much example of the bulk of quasi-crystalline materials. So this quasi-crystalline material you can synthesize by rapid solidification methods. So you can melt the material, for example, any composition of alloys, and you can get the quasi-crystalline in the form of ribbon. So this is the techniques, is that rapid solidification techniques. By rapid solidification techniques, you can get the quasi-crystalline materials. Other techniques is high energy ball milling. By the high energy of ball milling, this is also non-Euclidean processing techniques. If you take the alloy composition and do the high energy ball milling, you can get the quasi-crystalline fine powders. So this is a nice example, several examples. You can synthesize the materials using high energy ball milling. For example, here you can get. But I have done the work on aluminum, palladium, manganese. So we have grown this aluminum, palladium, manganese by a rapid solidification process, and we have tried to exfoliate these materials in DMF solution. So after 60 hours of exfoliation, we have got two-dimensional flags. For example, this material was characterized by XRD, and you can nicely see in bulk XRD pattern you have got all the crystalline plane or quasi-crystalline plane. But after exfoliations, only 3-fold symmetry axis was present in XRD reflection pattern. So this material was further characterized by different techniques, and you can see the TM detailed TM analysis. This is the two-dimensional flags, and this is the HRTM source clearly that this is the arrangement of along the 3-fold symmetry axis. And the STM image also, you can see the aperiodic nature. The aperiodic nature is clearly visible. And some theoretical calculation was also done with the help of Professor Douglas of the Douglas, and we have got the exfoliation along 3-fold axis only. So it means after exfoliations there is a lack of 2-fold and 5-fold. So, but the aperiodic nature is there. So you can say that this material is still quasi-crystalline nature. And in theoretical calculation, DFT calculation, this was not done by me, but some collaboration work. So you can see that aluminum, palladium, manganese is the most stable structure in this in two-dimensional shape. So further, we have done some work in the area of aluminum, cobalt, copper. So I have already said that this aluminum, copper, cobalt shows the decagonal quasi-crystalline structure. So this is the nice example of the decagonal structure. And after exfoliation, here we have got both kind of structure. For example, 2-fold structure also and 10-fold structure also. In excited pattern, you can see here only a particular peak is there, which belongs to the two-fold zone axis and also the tail-fold zone axis. So this material was detailed characterized with the help of AFM and SEM and also the XPS. And after that, we have mixed these materials with WS2, and this is a kind of two-dimensional semiconductor materials. And we have done the HER experiment with the help of electrolysis. So we have got very close performance of the platinum electrode, and if you compare with the help of this chart, this is around 140 times better performance of the bulk materials. So using this two-dimensional quasi-crystalline materials, we can produce the hydrogen at a very low volt. So it is a good materials for hydrogen production also. So another issue is hydrogen storage. So hydrogen can be stored in different form, in the liquid form, in the gaseous form, in the solid form. So if you compare here the different storage mode, for example, here is the gaseous form, and here is the liquid form, and here is the solid form. So the gaseous storage, the volume is required very high. If you compare to use the hydrogen as a fuel in two-wheelers, so it is very difficult to use because it is very difficult to put this high volume cylinder on the two-wheelers. So if you store the hydrogen in the cryo form, liquid hydrogen form, it is quite costly, and this is also difficult to put on the two-wheeler. But if we store the hydrogen in the form of solid, for example, here you can store the same amount of hydrogen and put the hydrogen storage tank just below the seat. So hydrogen storage in solid is quite important and quite useful. So many materials is already discovered, and so many work is going on worldwide. But this is a DOE target. If you store the hydrogen, for example, here storage capacity is more than 6%. This is quite useful. So we have just tried to show here the gaseous storage is a little bit dangerous. So if you store the gas, yes, part of hydrogen, if accident is taking place, whole vehicle is damaged. But if you store the hydrogen in the form of solid, so only particular place the damage is taking place. So hydrogen storage in solid form is quite important. One material is MgS2. For example, here the advantage of MgS2 is large deposited on the earth crust and low cost and very high light metal hydrides materials. And the storage capacity, if you see here, the Mg storage capacity is 7.68% and a high volumetric storage capacity. So the Mg is very beautiful material for the hydrogen storage, but there is some disadvantage. If you see here, for example, desorption temperature is quite high, around 400 degrees centigrade, so which is not feasible for practical applications. High desorption activation energy is also required. So how you can reduce the storage desorption temperature, for example, around 150 to 200 degrees centigrade, because at 150 to 200 degrees centigrade you can get this type of temperature by the exhaust gas. So when you can burn the hydrogen, you can get this temperature just like the exhaust, and if you use this exhaust gas to dissolve the hydrogen from the hydrogen storage materials, this is quite useful. And also you should improve the kinetics, because if storage kinetics is quite poor, so when you are going to charging at a hydrogen storage center, so it will take so much time. So everybody is not interested to charge, for example, 30 minutes and 1 hour. So you want to just store and charge your vehicle just like a petrol. So you should improve the kinetics, because kinetics should be very fast. So we need some kind of catalytic material to improve this kind of things. For example, here the desorption temperature you should reduce from 400 to 200 degrees centigrade or 150 degrees centigrade. Also improve the kinetics. So by using catalyst materials, you can improve this kind of things. So for example, here if catalytic material is there, this can release the storage hydrogen. For example, here red color balls is the hydrogen atoms. So you can release the hydrogen from the hydrogen storage materials. So we have used the quasi-crystalline material as the catalyst. So this is the example of Al3Fe catalyst, isostatic phase. So we have released this material with the help of NaOH, 2H or some alkaline solution. So from the surface, for example, here is the cluster of LCFE crystalline materials, and here is the cluster of after leaching. So you can leach this aluminum. So there is a copper and iron distribution on the surface of crystalline materials. And you know there is no phase formation of copper with iron at room temperature. So both the catalytic element is present in the form of atoms when you are using the crystalline material as a catalyst. So this is very beautiful catalytic material to improve the problem related to Mg, H2 hydrogen storage materials. So this material was characterized with the help of TEM and also EDAX. So you can see here in the EDAX also the concentration of copper and iron is going to improve. For example, here the concentration of copper and iron is very high compared than the bulk. In the bulk crystalline material, on the surface there is a lot of aluminum is there, and after leaching this aluminum was removed by NaOH or KOH, and you can get the copper and iron concentration. And there is no phase formation. Means copper and iron is present in the independent form. So if you see here this desorption curve, as such the M2H2 desorption temperature is quite high, more than 400 degrees centigrade. But if you use the crystalline material as a catalyst, the desorption temperature reduces around 215 degrees centigrade. So after using crystalline materials, you can reduce the desorption temperature from 400 degrees centigrade to 250 degrees centigrade. So this is very good catalytic materials to improve the property of hydrogen storage materials, especially for MTH2. And if you see the kinetics, hydrogen storage kinetics, you can see here in just in few seconds you can store the hydrogen around 6 weight percent. So after using crystalline materials, you can improve the hydrogen storage property in both directions. For example, reduce the desorption temperature and also improve the hydrogen storage capacity at the kinetics. So for example, here you can see here 150 degrees centigrade, even we have got around 5.58%. And at 100 degrees centigrade also, here kinetics is a little bit poor, but if you see here the storage capacity is around 5%. So this is very good storage capacity and very close to the DOE target limit. And if you see the cyclic stability also quite good. And we have done the experiment around 50-100 cycle. So in 50-100 cycle, the desorption capacity is little bit reduced, but it is quite useful. And if you see here the plateau pressure, for example, in the PCI experiment, the plateau, yes, I will finish in 5 minutes. The plateau pressure is around 6 to 5 atmospheric pressure. So this atmospheric pressure is not very dangerous. So this is very nice material to as a catalytic material. So this is the detailed mechanism. So now we have tried to use the high entropy materials as a catalyst. So here we have tried to synthesize some other materials. So high entropy means their mixing of entropy is quite high. So many papers is already published regarding the hydrogen storage materials as a high entropy. So we have synthesized this particular materials, titanium 20, zirconium 20, and vanadium, chromium, nickel in our laboratory. So this is the synthesis process of the high entropy materials. And we have also tried characterize with the help of XRD and other characterization techniques. We have got the C14 log base in this particular high entropy materials. And we have tested this material as a hydrogen storage material. So storage capacity is quite low, but kinetics is quite good here. So storage capacity is around 1.8 weight percent. So further we have used this material as a catalytic materials for MPH2, of course. Using this high entropy materials after leaching is not performing well, and we have reduced the temperature from 400 to around 320 degrees centigrade. So on the basis of this all kind of hydrogen storage materials and also hydrogen productions, the Banaras University has developed several devices. For example, 2-wheelers and hydrogen fuel cooker, 3-wheelers, 4-wheelers also, and in the leadership of Professor Srivastava. But I can conclude that if hydrogen economy can be realized when we can develop the good process of hydrogen production and as well as hydrogen storage. So I would like to thank Professor Srivastava because he has introduced me in the area of hydrogen energy. And also Professor R.S. Tiwari and Professor Anku Mukhopadhyay, my co-supervisor in PhD, and other collaborators from University of Liverpool and also University of Rice and Japan Science and Technology Institute are few students who have involved in this work. For example, Satish, Sunita Pandey, and Abhishek and Yogesh. So I would like to thanks for your kind attention.